Yeah, it's hard to follow Ben's, wonderful, comprehensive talk, but I'll try to touch up on some of the sensing issues if I can. Okay, so here is, sort of the outline. Somebody told me that if you're gonna give a good talk, tell people what you're gonna tell them, and then tell them what you told them. So this is the first part. So I will try to motivate the sensing challenges and solutions in the mobile health space, and try to highlight both challenges and opportunities. Then, since the talk was framed on foundation models or foundational models, how this new paradigm in machine learning and AI is changing the way we do business in mobile health. I like to sort of define what these foundation models are and perhaps contrast them with the classical machine learning workflows that we were working before. Then, I want to just try to highlight how are they trained, what are some of their pitfalls, and what do they actually learn, these foundational models. Go through some of the ones that you might find useful in your projects, research down the line, and let's discuss how one can adapt these paradigms for the inference tasks that might be interest to you. Present few case studies, just so that we have something more concrete in our mind how these things are used in the mobile sensing field. And I want to sort of conclude with some pitfalls to avoid and some deployment constraints when we try to implement these foundation models at our edge devices, at the wristbands and at the phones, etc. So you are all here because you believe in the promise of the mobile health. So, but still, I want to maybe underline what the role of sensing, what sensing plays in the mobile health system. So in United States, we spend close to 18% of our GDP to healthcare, and most of the spending goes to chronic care management, like management of diabetes, heart failure, and substance use disorders, etc. And what might be striking with this this flow of money to these expenses is most of these conditions are actually driven by modifiable behaviors, like if we had better physical activity, sleep, diet, stress, medication adherence, and substance use, we might be able to avoid these chronic diseases for a longer time. So but what is the mobile health sensing changes in this story is it changes what is measurable. So, like the slide says, continuous streams of physiology and behavior will let us study the disease mechanisms at population scale. Maybe we can then identify modifiable risk factors, and more importantly, use those sensor stream to intervene at the right moments that they matter, which I'm sure other experts in the faculty will do a better job in explaining. But this promise is enormous, but it is somewhat tempered by the challenge of can we actually make sense of these sensor measurements in real time at scale over different population, over different devices to make reliable decisions. And this mobile sensing in the wild, in the natural environment, is not just for chronic disease, modifiable behaviors that might lead to chronic disease, but it's built everywhere. For example, just to give another example, so as people in academia and elsewhere, we are interested in understanding the cognitive processes that explain the engagement and learning of our students. Okay, so and if we had better observations about how they orient themselves, their gaze, their behavioral cues of attention and focus, whether they are fidgeting, etc., and whether they are stressed arousal is present. And maybe we can correlate these with brain signals and understand, new insight to the cognitive processes that underline the learning process. So again, the core idea is to sense subjects when it matters, when they are learning, when they are out there in the real world. So, and we are living in a fortunate time, where we have sensors almost for every body function and subsystem, especially monitoring the autonomous nervous system, which regulates a lot of our stress response, etc. We can see how we are physically active, what we are actually, paying attention to, our focus attention, and of course, other heart and vascular systems, and more importantly, perhaps the brain and emotion states can all be measured with some sensor available at reasonable cost. But the insights from those sensors are much harder to obtain. So it's not clear whether we can take these raw sensor streams and create the behavioral and physiological markers that will help us in our research. So the key challenge is to take the sensor data and turn it into biomarkers that we could use in studying disease progression and etc. So, very simplistically, the chain has in the mobile health from sensing to interventions follows like this. So we are monitoring, our physiology through sensors that we are wearing. For example, a wristband can provide information about heart rate variability, your motion, your gestures, eating, etc. All those are providing you accelerometry, gyroscope, and pulse plethysmography that provide this continuous visibility to the biological system. Then we typically have some AI ML chain that takes those into biomarkers of behavior and physiology, whether we are, what our eating habits are, what are we doing in smoking, what are some of the times we are stressed, and what are some of the physical activity. And then maybe we can understand this relationship between chronic disease progression and these habits, and then maybe we can intervene at the right moments. So the key piece here is, again, the AI ML piece, which has been taking the sensor data to the biomarkers that we are interested in. And, I want to go through one example, which I like, which shows us the classical machine learning workflow for this behavioral sensing. So this is, sort of a project ideated by our host, the Honorable Vivek Shetty, that told us that, in the United States, half of the adults are suffering from periodontal disease. And if we could infer the timing, duration, and the quality of brushing, then perhaps, we could provide, again, the right feedback and put people into better trajectories, which might not only help with their dental health, but as well as all the other implications of the periodontal disease. So the idea is basically here, you can see it. So we have a subject doing some motion, right? So if you look at it, perhaps you can convince yourself that this particular oral health behavior is flossing. And the idea is, of course, it's somewhat easy to see when you are animating it in 3D, a full skeletal model. But can you infer this from just the wristbands you wore on your wrist? If you just look at those accelerometry signals itself, it's not that easy to look at it. Anyway, so okay, here it is. So if you just look at the wristbands itself, it's not so clear. So the project was, can you tell all the oral health behaviors, how long they last, whether at what time are they occurring in the day by continuously monitoring an object. So they were wearing IMU sensors, which provide 16 hertz accelerometry, how your wrist is moving in space, accelerating, and 3-axis gyroscope, how your wrist is rotating, essentially. And here comes the painful part. To power this study, there was labeled data collection of 2,787 hours of data collection, where 25 participants wore the bands over 192 days, and which provided enormous data that both powered the training and testing of the algorithms, the machine learning algorithms that maps the sensor data, accelerometry, gyroscope, to the decisions about the oral behavior, whether they are flossing, when are they flossing, how long are they flossing, and brushing, etc. So the classical workflow is you do some feature discovery, you try to take those 6 streams of data to something more meaningful in the task you are trying to solve, and maybe sort of you are keying on actual orientation of your wrist and how it moves in space. So this pronation, supination of the wrist itself, and then take those through a classical ensemble learning method of machine learning, create a classifier, and then test and validate that classifier, and which is shown here. So which took 2 years of data collection, algorithm development, sensor deployment to get to a place where we can claim with high accuracy that we could actually tell people manually toothbrushing and flossing with string, we can tell how long they are doing and precisely describe this process. But again, a lot of resources, because essentially you are starting the problem from scratch, as if you have never seen somebody brush. You collect the data because you are seeing that brushing behavior for the first time on the wrist, and you need this machinery to be able to make sense. So this is now 2019, about 7 years ago. So what are the current paradigm to this same problem? So the foundation model approach to behavioral sensing is a bit different. So you go out there and try to find for the modality you are interested. In this case, we are interested in the wrist-worn IMU modality. So there is a UK biobank-based model of a HAR that is trained over millions of data points that provide an encoding, basically a different representation of the input signal. And this foundation model comes, the weights are available. You could download it and then take your windows of data, push it through, and then get to a manageable representation or a feature space. And then you do a training with a simple classifier, sometimes as simple as linearly combining the features provided by this foundation model, and map it to manual brushing, flossing, dental disc usage, electronic toothbrush. So what is the advantage here is you can learn from much fewer labeled samples, because you are training a much simpler classifier. You already have the features evaluated for you. All you need to do is close the final gap, because the data was trained without your task. So you still need to provide few labels to close that gap between the feature space and the downstream task. Of course, you still need data to validate and evaluate your system. So I think, now we can sort of, look at this question a bit more carefully. What is a foundation model? So foundation model is, described, I'm a sort of a very, typical guy. So what is it at the end? It's a large, deep network that is pre-trained once on a broad corpus of data using an objective that does not require human labels. So it trained on data only, essentially, to produce representations or features that transfer to many downstream tasks that were not even specified at the time of training of the foundation model. And this transfer to downstream task occur with little or few training samples. So what we call zero and few shot learning approaches. So this last point is particularly important because if we had still a lot of samples, this is perhaps, we can call this as transfer learning that we've been doing for maybe, for much longer time. So the key point here is we are able to learn very quickly for new tasks using few samples. And that's exactly where mobile health sensing lives, right? So for a field like ours, behavioral science or mobile health, careful labeling is very expensive. And sometimes it could be even impossible in the field. So therefore, this is not just a technical improvement that, it sounds nice, foundation model, but it's a change. I think it will change basically what studies are feasible, because a lot of more studies could be feasible if we remove this labeling part out of the picture. So what is, again, three ingredients of the foundation model building? So first, we have a large scale and diversity of data available from many different subjects, from many different demographics, as well as different devices that provides this raw sensor data. And then we have this pre-trained neural network that we are training to map those streams of data to a representation space that we will use later. But during training, we don't know what people are going to use this model for. So the key idea is we're going to train this model with a self-supervised pretext task. So it has to be a way to learn without labels. And finally, we need a network structure deep enough that can absorb the scale of the data that we are giving. So it has to have enough weights, basically, to be able to learn all the peculiarities of the data we present. So it requires these three components: scale. We need a self-supervised version ability to train it, and third, we need a large enough model to be able to absorb that information. Current models are favoring transformers, but I think that's not as critical as the first one. The power of these models are coming from the scale and the diversity of the data we feed to them. So if you look at, here are some foundation models that are relevant to our field, mobile health research. So we have some models for studying sleep. We have some models for accelerometry. We have some models that combine accelerometry with pulse plethysmography, etc., to provide more variable sensor suite models. And then, and finally, we have vision models that take images of various scenes, especially humans, to provide information about that modality itself. But the key point is, look at it: 40 million hours. We just complained about 2,700 hours in our study, which was large for training something for one purpose. But here the amount of data is 2 orders of magnitude larger than a classical one. So these models are going to be trained by large corporations, centers like university, etc., centers that has available resources to collect that data, curate it, and able to have the GPU resources to train these models. So we talked briefly about we need a way to train these models without knowing what the task is. So one might wonder, if I don't know the task, what am I training it for? And I think Ben already told us in the case of large language models, the pre-training phase is actually somewhat simple. You try to you try to guess what the next word is, try to learn to predict what the next word is from a context window. Similarly, people start looking at this problem in the sensor stream, thinking of, okay, I have some sensor streams. If I see this context window or this prior measurements, can I predict the next 30 seconds? Let me train so that my error is small in MSE or some other sense to in the future forecasting prediction mode. So an easy generalization of the LLM idea to the sensor domain. Perhaps a bit different in our sensor domain is we don't have just one modality, not just text, but we have PPG, we have accelerometry, we have temperature, and etc. So these are sort of providing different channels in parallel. So perhaps we could also try ideas where we block one channel and try to use the other channel to estimate that, right? So that's a potential idea here because, the multi-channel aspect is new to the sensor. So that's sort of what we call prediction with random masking. So we mask, we delete some of our signal and try to use all the other signals around that window to try to predict that channel at that time, giving us some ability to do cross-channel inferences as well. So that's, and again, both of these doesn't require any labels. Just the data itself allows you to train these. And, there are, sort of variations of ideas that based on this encoder, whatever it's doing, has to be able to keep things that are similar in morphology, similar in heart rate, similar in accelerometry together. So the idea is you take your data, you augment it, or you modify it by some transform. That, for example, the signal gain could change over time. So you apply some attenuation or amplification and create more segments of your data in addition to your real data. And then you have data that is coming from a different subject, from a different time. So hopefully you say, my encoder should be such that any version, any augmented version should live closer in the embedded space, and any new subject on a different time should stay away from it. So this contrastive loss is try to reorganize the embedding space to keep things that are similar in the signal space in morphology, similar in the embedding space, and push them apart if they are representing different morphologies, etc. But the key point is, maybe the details are not that important. None of these require anything but the signal. We could train these models with just using the signal. As long as we have large corpus of data, we are able to train these encoders or the foundational models. So pre-training at the end achieves this, right? So it creates a representation space around the structure it observes in the data. So heartbeats with similar morphology, they cluster together. If people walking together, if people are walking, their signatures map to a different place than people who are running. The sleep stages, whether I am in deep sleep, the REM sleep, etc., should cluster themselves based on the sleep stage I'm in. And hopefully, the motion artifacts should factor out from the system so that my system becomes invariant to those artifacts. So let's look at some trained systems. So this is a trained system for sleep, an open sleep model. And you can see that here is a sort of a visualization of the encoding of EEG, ECG, everything that they measure in sleep studies. This huge stream is mapped to a lower dimensional representation space. And this is yet even projection of that representation space so that we could sort of begin to see some clustering. We see that difference, although we didn't say this, different sleep stages clustered the different places in the representation space. There was no mention of sleep stage. We just gave the data, and the network sort of learned basically this underlying structure and shape the representation space to reveal that. And as a result, although the sleep model is trained unsupervised, it does actually very well in various subtasks. Not only sleep staging, but also predicting disease, hypertension, diabetes, etc., from the same data, because the representations are keying on some structure present in the data itself. Similarly, this is the a scalable variable foundation model, which is trained using random masking strategies, and we can see that how different activities cluster themselves naturally. Nobody said these activities are even present in the data, but after the fact, probing, you could see where activities fall in the representation state. The data itself organizes to where different activities are organizing to different regions in the space. So, and therefore it does well in activity recognition without being trained in. So I think this provides us the insights. Why do we need few examples to train on top of a foundation model? Because it already self-organized itself to provide clusters corresponding to various tasks. So all I need to do is basically have few labels to figure out where am I in the representation space, so that I can draw a boundary or region to classify as the particular task I'm after. And so sort of that's the key idea is, although I don't see it, my task is already clustered itself. All I need to do is figure out which region belongs to the task I'm interested in. Which region does it belong to manual toothbrushing? It already seen, basically some information about people brushing and already clustered it in a way. All I need to do is figure out where it is for me to label it with few data points. So these, at the end, these representations capture morphology of the waveform. So the beat, the quality on the artifacts, and can separate walking from running, let's say. And it can figure out the physiological state, whether I am stressed or not, asleep or awake, just by self-organization. It does have information about health conditions, and perhaps surprisingly, it has demographics and subject identity in there too. So since nothing asked it to be privacy sensitive, etc., so this identity is already also clustered. It's so that this guy data appears over and over again. It learns to cluster things based on identity. So therefore, one has to be sort of careful when evaluating these systems. But so we need to understand that we should not identify the person, but actually the condition of the person. What they might miss or misrepresent, rare events that are underrepresented in the data. So if there is a very seldom appearing arrhythmia, that's not going to be there. And plus, it might key on some device-specific artifacts. Suppose some some wrist-worn device does not fit to young children as well, right? So therefore, it's going to look very different because that device is sort of maybe rotating on the rest for young children. So what I'm measuring from the device is nothing to do with actual condition, but I might be keying on the figuring out whether people are young or not based on just how much this device is rotating. And obviously, if I take that foundation model to a different device, which doesn't have this problem, I might be misled and might have terrible real-world performance. So one has to understand these pitfalls exist when you train with no labels and no. And again, to me, this was somewhat interesting, although we haven't really dialed down the demographics. After the fact, you can see that actually the representations capture gender, capture age, and as well as the subject identity. So, all these privacy concerns about the foundation models not revealing are still standing. And this also tells us that, if a certain group or age or gender is underrepresented, so the classifications, it's everything that we build over will be affected by the quality of that foundation model itself. So one final comment, we said the key point of these foundation models is their scale, the amount of data they consume. But the scale comes not only in the data size, but how much compute time you could spend on tuning the model further and further to do in that pretext task. And also, what kind of model do you deploy? So, the industry level studies with hundred thousands and more subjects, millions of hours, revealed scaling better performance in all three dimensions. So compute, if you have more compute, you're going to get better performance. More data, training data, you'll have more performance, and more bigger models will in general yield better performance as well. So for most of us that are not at the center level, university level, or the corporate level, pre-training these foundation models from scratch is not really feasible or advisable for most application domains. So our job is to use the foundation models to create systems that we can deploy for mobile health interventions. So the landscape of sensor FMs for health. So we can broadly, again, just give you a way to, get the taxonomy in your head. So there are the biosignal FMs. These are single modality systems. Then we have the multimodal variable FMs, which try to combine PPG, IMU, etc., all variable streams that a wristband provides into a single model. Then we have vision foundation models that take imagery and then, make sense of these, especially in terms of understanding how humans present themselves in that space. For sake of time, you will have access to the slides, I'm assuming, so you could always read the tiny details of different ones. But again, the different taxonomies are, we have single signal models trained on a single large biosignal corpus. So we have PPG models, Papa J, Pulse PPG, a model that is trained by researchers from the MDOT, Jim Rake and Santosh Kumar's group, and another PPG model. So these are trained on both field and clinical data. And we have ECG models that allows you to take single lead or 12 lead ECG and create a representation for you to look for cardiovascular parameters. And finally, we have accelerometry models that are UK Biobank based, which looked at 700,000 people's data from wrist-worn accelerometers of various kinds. So typical downstream tasks that you could solve with these are, you can look at heart rate variability from PPG and ECG. From ECG, you could look at cardiometabolic risk, atrial fibrillation, and etc. And from the IMU, you can get the precise activity recognizer, and perhaps looking at respiratory rate as well. So this is where we start if our application is a one sensor, single modality. So we have multimodal FMs now emerging. So this is where the field is going, training basically with multiple channels. So some of these are for sleep science, which always used multiple streams in a clinical setting, EEG, ECG, EMG, respiration, to get sleep staging and some disease recognition. And now these are propagating into consumer level variables, which also provide multiple streams, like the accelerometry, pulse plethysmography, galvanic skin response, how much your skin is conducting, temperature and altimeter, etc. So these are the second class of multimodal foundation models. And now a new, a subclass is emerging, which are behavioral foundation models. So these are sort of working on derived features. Instead of doing the raw sensors, these are trained on step counts across the different, say, hourly step counts, the sleep durations, the heart rate variabilities you get at the end of every day. So things that are summarized across the longer time scales. But again, idea is if you have access to those kind of data streams, can you create a foundation model for this? So the trade-off is we can typically with multiple streams, we can do more powerful inferences, but now all the data goes in and then you get one common intertwined representation space. So it's very hard to figure out if you find a signal or be able to tell, say, a certain disease risk. It's not clear from which sensor it originates from. Tracing it back and what feature it remains to becomes much more challenging. So explainability becomes a challenge using multimodal measures. So looking at the final vision models, these are sort of looking at thousands and thousands of photos curated for example, activity, object, and scene recognition. So we use these Dino V2 and other models when you are mostly interested in the environment. What is this, the environment this person is at? For example, is he facing some advertisement, and can you recognize smoking advertisement, and does that really affect his behavior? So if you are interested in characterizing the environment, so these vision models are very, very powerful. Zero shot gives you classification of the objects. Then, we have the human-centric meta-sapien model, which from 300 million human-centered images that can train again in a completely in a pretext task that doesn't require labels. So they trained using 300 million images, learned how a human shape evolves over time, etc. And then they also trained linear heads, inference heads, lightweight inference heads that can do body port segmentation, depth from a single image, the surface normals, and especially the pose of a person. So give a single image, you can get a fit a skeletal model from a single image in an arbitrary naturalistic environment. So now, our job is to use these foundation models, after we learned what their modalities are and what their capabilities are. So the paradigm now is we can do 0 or 5-shot transfer. So we use the pre-trained representation directly without training anything. So that's sort of maybe could be the case. I just take a sample from my sensor and then go map it to the representation space and say which label sample is closest to the one I have. So I need few samples to be able to do that because I still need to look up which is the closest one, but I don't need to train any new classifier. Or it could be genuinely zero shot. I might have no labels. For example, I can see how well the representation, how close am I in the representation space to the training data in the corpus. So I can see this distance. If I'm not close, then maybe my signal quality and artifacts are such that I am outside the data that they trained the system. So it could be a zero shot, no label signal quality measure. Or these models are typically not only trained to provide the representation, but they come with some inference heads for activity, heart rate, etc. Maybe I could use those directly and put it on top. When is the paradigm one more perhaps suitable is when we have very few labels per class. We don't have a lot of label data. We want a fast prototyping just to see if this idea is worth exploring. And when we need to personalize a new device without collecting a new training set. Paradigm 2, which is the default approach. They give us the encoder. I train a small model on top of the embedding. They give me features. I do even my classical statistical uh, inference on top of those. So we pass each window of my signal through this encoder. I get a vector, and I use that vector to make my inference. I can do a linear probe. I can take a linear combination of those features to map to the particular class that I'm interested in. Maybe, for example, create a linear head for oral health behavior. And I could do one of the classical methods of logistic regression, etc., or any of the others that we know from classical machine learning. When we can use these, if we have 10 to a few hundred labels, because we still need to train that tiny classifier on top of it. But sort of it's nice because it provides all the classical features of interpretability, of coefficients, what feature is more important, odds ratios, etc., which we might care about. And finally, if you have enough expertise and compute power, you can train the encoder itself also for the task. So you can say, they give me an encoder to start with, maybe I can fine-tune it. Of course, this would require GPUs and somewhat more labels. And we have to be careful of not overfitting to the case we are doing. So the classical words that you might be looking at, that low rank adaptation adapters, are trying to find the middle ground. They say, I'm not going to modify the entire encoder that these guys trained. I'm going to encode a small fraction of the weights that are most relevant to my task, so that so when we use this linear probe, performance is perhaps not that good, and maybe our signal or sensor is distant from their pre-training distribution of people and the devices. So I like to do a few. I'd like to see the time to make sure. Okay, I'm not bad. Okay, sorry. I just want to make sure I'm not overrunning the time. Sharing again. Okay, so I'm going to go over just a few, use cases, that might give us a concrete idea what exactly these foundation models come into play. So, for example, right, conditions like ADHD, anxiety, and sleep insufficiency can, influence how children learn in school, moment to moment, hour to hour, across the school day. So, and this has some, consequences of academic achievement, social development, and long-term health trajectories. But the mechanism, that we like to interested is, we have to figure out how are they paying attention state in the classroom? How are they being engaged? How are they being, stress arousal is happening when they are having activities together or with the teacher. So right now we rely on teachers' ratings, self-reports. We go to the parent student data and try to get it, but we need more objective, continuous, ecologically valid measures of attention, arousal, and motivation as they unfold in the learning process. So mobile health is, maybe a natural choice here. And the idea is perhaps we can instrument these classrooms with, some sensors and give the students some, wristbands, so that we can do two things. We can get their orientation and their torso orientation and gaze from cameras to localize visual attention. Where are they looking? Are they facing to the teacher, facing their partners when they are working activity together in a natural setting? And then pair it with some physiological and movement sensors to infer the arousal and fidgeting and other motivation deriving that attention. So we're going to employ the meta-sapiens model. So previously, for example, in the oral health study, you've seen that beautiful diagram where the 3D animated object was, flossing. How did we get that? That was a $500,000 facility with 46 cameras looking at markers while I am flossing. So that was, sort of me in the virtual space captured from 36 cameras. So obviously that's not a feasible one to deploy in the classroom. So we are going for a much simpler approach, perhaps just the teacher's cell phone camera, and employ one of the foundation models to get to the orientation vector that we are interested. So we are looking at this meta sapiens model trained again over 150 million images of humans, and it comes with 4 heads, 4 inference heads to be able to do pose estimation, skeletal gesture. It can segment it into different segments: hair, face, torso, hands, etc. It can provide a rough 3D depth information and some surface normals that even provide some information about the exact orientation of the surfaces on you. So we look at simply the skeletal estimate. So here's students, seen from a single camera, pushed through the meta sapiens model that, with open source weights. It's a 2 billion parameter model, which performs quite well, zero shot, just directly feeding your images and creating the skeletal model. So from the skeletal model actually doesn't have a torso vector. You could calculate it from the 4 corners and sort of try to get an orientation vector of the torso from the 4 corners. But this is somewhat misleading. As you see, that vector is not that good actually, because it's actually a 2D skeleton, meaning it's something that is drawn in the 2D model. It has no idea that things are actually in 3D. It's just giving us on image coordinates where the points are, and then you try to sort of reason what the vector might be. Okay, so it has limited information about the 3D orientation vector of the student. So as a zero shot model, this is where you stop. You live with what this model gives you. But you could also build on it. So you could have 2 cameras. 2 cameras gives you 2D skeletal models, drawn here. And then you have 2D skeletal models. You know that they correspond to each other. With a little bit of computer vision and linear algebra, you can actually solve the problem of what is called camera-to-camera calibration. You know where the you will discover where the 2 cameras are and use those information together to get a 3D vector. So now we have basically a 3D vector, much better from 2 views, that is building upon the zero-shot sapiens model with just some linear algebra and computer vision knowledge, just showing the potential, what one can do very quickly without spending $500,000 on a motion capture system. So this in principle could be the teacher's camera, right? So that was maybe case study 1. Case study 2 that always interests me is heart rate and heartbeats and heart rate variability. So there are multiple technologies to monitor heartbeats, ECG being the one of the well-known ones, where you have here shown as the ECG stream. So that's your heartbeats, and it's actually what you see in ECG is the way the heart polarizes before it beats. So then you see that high electrical pulse when the polarization goes across your heart, and then your heart actually moves. So a lot of our autonomous nervous system response is not hidden in the heart rate itself, but in the heart rate variability. Meaning, although, right now, for example, say my heart rate is beating 60 beats per minute, it doesn't mean it is beating every second on the second. Sometimes it's shorter, sometimes it's longer. That variation is basically grounded in the interplay between the sympathetic and parasympathetic systems of your autonomous system. One of them, the sympathetic one, is trying to make you go faster, and the parasympathetic one is trying to make you go slower. And those challenge, as you get external challenges to your system, those systems play around even more frequently leading to increased heart rate variability. So as a seasoned speaker, I might not raise my heart rate. My heart rate variability will be certainly raised because while I'm trying to get the demands to my system, trying to give this talk both mentally and physically. So this is important. Both are important measures. And unfortunately, if you don't have ECG, that's not that easy to see. So this is what the wristbands see. You have basically, in principle, different LEDs shining light to your capillaries, and then you are looking at the reflectometer. So here is how the beats look like. Harder to figure out where exactly the beats are. There are some places where beats look like twice. Not true. It's just motion artifacts, etc., come together, try to confluence what the photoplethysmography signal is revealing about the underlying heart rate. And in the field, you get a lot of the time these double peaks that don't exist, just it's there because of the motion artifacts. So you will see heart rates that are twice, third times the actual heart rate because you are capturing these pulse beats that are not real in life. So that's heart rate computation is confounded by many factors, including motion artifact, noise, and the variations in the way the sensor touches to your skin interface. So not a easy problem by all means. But we over the years we developed both many methods, signal processing and others, try to combat these motion artifacts. But so the new era is training foundation models for PPG data. So there are couple here, again the second being from the M.Dot Center. The first one trained on public PPG data sets, mostly clinical, and Pulse PPG is trained on data from the field, about the same number of hours, 55,000. Again, somewhat modest compared to some of the data sets we talk about, but perhaps enough to capture all the variability in the PPG modality, single modality. So the idea is foundation models are, since they are trained on the field model, maybe they can absorb all the effects of the noise, motion, and variation in the encoding stage so that it gives us encodings that are invariant to these motions. And therefore, all I need to do is a simple downstream model that can focus on the task of heart rate and heart rate variability measurement. Here is something we tried outside the data set that this particular Pulse PPG actually was trained on. And then we will look at basically just directly the performance of the inference head provided by Pulse PPG. We see that the y-axis is the ground truth, x-axis is the predicted heart rate, and they are somewhat in good agreement. Of course, there is some error for field data, which is about 8.9 beats per minute mean absolute error sense. So one can take this. This was just training a linear head for our data. So we took the Pulse PPG, we take their structure of the heart rate estimation head, and we fine-tune just the linear head, just the second part to do well on our data. We achieved 8.94. And if we take the entire structure, actually Pulse PPG has a somewhat a simpler, smaller structure of 1D resonance, which you can train end to end. And we were able to reduce that error up to 4.46. And on the right, you can see how it performs on the left and right wrist. This took less than a day, just to take the Pulse PPG and sort of fine tune for our use case. So much more faster cycles than before for research. Okay, so that's the good news. The bad news is the heart rate variability. We talked about not only heart rate, but the variability is also important. When you try, this simple approach of training a head for estimating heart rate variability metrics like the standard deviation of R2R intervals, it doesn't perform that well. Again, on the Y-axis is the ground truth, x-axis is the predicted. Especially for low signal quality, it's essentially randomly guessing. And for higher signal quality, it does have some performance. But this simple approach of take the pulse PPG and train a linear head to go directly to the answer is maybe not the right approach. But we have seen the base beat detection performance of the foundation model is strong. So perhaps we just have to figure out a better way of inferring on top of that inference structure, maybe reasoning over potential likely beat sequences to close the gap, the performance gap between what we want in heart rate variability. So again, it's good to mention not everything is solved problem. These foundation models are quite strong in their representation capability, but training something on top of them is not always trivial. So some pitfalls to close the talk. So some shifts between the devices that they used in training versus the devices we use in our studies might lead to deterioration of the real-world performance that we get in our studies. We are using a different wristband, different firmware. We might have a different LED wavelength. Our photodiodes might be representing a slightly different one. Maybe they didn't capture all the variability in the device space, and therefore you might be subject to device shift. There could be population shift. Maybe our particular population, say children, age school children, is quite different than what they trained with. So of course we're going to suffer from that. Other things could be clinical versus free living in the wild, and skin tone diversity, another famous one for PPG. And finally, they might have been deployed in different seasons, different weathers, different geographies, which might lead to some biases in the estimates we get. And finally, a lot of the time, these large studies, participants are encouraged to wear, through various means, and they wear the devices a lot better, a lot more uniformly than what we wear the devices in our studies or in free life. So therefore, the sensor data that the foundation model sees could be different than the real user from one of our studies. So we need to be sort of ready to fine tune, perhaps end to end, to deploy on a new population, on a new sensor platform. Another pitfall that I see is, the foundation models are giving a representation, and then we are training a linear or a simple inference head on it. A lot of the time, these raw outputs from these simple structures are not really calibrated out of the box. They look like they are soft decisions. They give us a soft probability, but they are not reliable because they are not calibrated. So one has to be, sort of aware of that fact, and make sure that they calibrate, even if it's simple methods of temperature scaling, isotonic regression, which are easy and computational cheap. We need to calibrate our measures so that we can use them as soft measures. If we are going to intervene with someone, we better be sure about the probability that we are wrong about the behavior that we are sensing. And finally, maybe go even higher and do correct uncertainty estimates. Finally, to bring it home, we need to deploy these systems somehow. A lot of the things we discussed was post-processing. We conduct the study. It's time to process our data, and we can use foundation models on laptops, etc., and even cloud devices. But if we are doing real-time interventions, we need to be able to sense this person is very stressed, so that we can provide the right intervention. So we need to run these at the edge, close to the subject. Two options: phone versus the edge device, maybe the wristband itself. So this is a typical chain: is to run wristband, push the data to the phone, run our algorithm on the phone. The good thing is a lot of the variable sensor models are already sub 100 million parameters, not large, easily runs on the current phones. And we can even do it real time, all the time, as long as we can stream the data to the phone. Some of the vision models require substantial resources. We could run, smaller parameter models of these vision models on the phones, at least maybe not in real time, but a frame by frame basis. And finally, we can think of implementing these on the edge devices itself. Not a trivial exercise. If you think about what is on your wristband, what are you running? You are running essentially a microcontroller level device, an ARM device with very limited computational capability. But more importantly, you don't have the memory. You have about couple megabytes of RAM and maybe tens of megabytes of flash memory available to you. So you cannot store large models either in real memory, in volatile memory, or in the flash memory. You have to distill your model to a much smaller student model. Okay, and there are ways of doing this through quantizing the foundation model and distilling it to a model that is available to be run on the wristband. And perhaps with tight quantization, we could run some of the single modality sensors, pulse, PPG, etc., through distilling them too. But this is still outside the realm of the transformer-based models. There is no foreseeable feature where we can fit the transformer models to these edge-level devices. And of course, if we could do it, what would be the benefits? We will be always on monitoring. We don't need to have our phone with us. Our devices will be always on our wrist. They will be always monitoring, always computing, always finding the representation and figuring out the various biomarkers. And this would be helpful for privacy sensitive deployments where we don't want to store the data on the phone, and so that we just provide the inferences itself. And it might help also with our battery management. So to summarize, what are the principal takeaways? So these foundation models with pre-trained representations reduce dramatically the labeled data requirements. And that's where we are a lot of the time in mobile health. We don't have ability to human label, large corpus of data. So we need to, a lot of the time, work with small label data. And here, these pre-trained representations could be useful. This large data space training will help us generalize across devices, populations, and settings. And this allows us basically a structure that we could deploy at edge devices. And hopefully, given the models were trained in free living conditions, hopefully that will broaden the range of research questions we can answer with the current techniques we have. Thank you for your attention. And I don't know whether I have time for questions or not, but I'm always available at the email.
Emre, thank you very much. We'll take a question, and I want to give these scholars a well-deserved break. Are there any questions? Raise your digital hand. I should point out to the scholars that Emre is a tremendous resource to the mHealth community. He's a very practical faculty engineer, and several of the graduates are actually using him to back in the biosensing aspects of their projects. Very generous guy, as I know him. I hope you're still the same, Emre. And
engineer, yeah, I like the engineer and the faculty. Yes, exactly.
Yes,
I'm a practicing engineer. Yes.
Yeah, practical translation. Emre, thank you again for joining us.
Thank you.
We'll give the students a break, scholars a break. We'll